All right, guys, welcome back. Now we are going to read the paper Sentence Birth. I have explained the concepts to you in the earlier part of the morning, but now let's go back and look at the original paper. It's an old paper by modern times. It feels almost ancient history, but it was a landmark paper. So it is really worth studying it in detail. And one second, my screen is touch sensitive, so things are floating around. I apologize. Okay, this paper, I'll give you a backdrop. At that moment, by the way, this was a 2018 paper. I think this version is or maybe we won. Okay, 2019. So yeah, at that time, what had happened is transformer architecture had been discovered in December 2017. BERT, and I'll explain what BERT is. I sort of explained as the box through which vectors go in and embeddings come out, had been discovered. I'll tell you a little bit about BERT. The main problem with BERT was, or the power of BERT was, let me just say BERT. The thing with BERT was that you could feed it, you had to feed it to sentences, sentence ones and sentence two. Now, sentence two was optional. Sometimes you would feed it, sometimes you wouldn't. You could choose to leave it blank. But for the case of search, well, it would, and then it would produce all sorts of embeddings. For each word, the cow jumped, moon, and then something. For each of these would go in, and for each word, an embedding would come out. And then you would append a special token called CLS, for obvious reasons, for classification. And there's a technical reason why you do that. But the CLS token, the output, the embedding for CLS was special. In the language of attention, which you will, the theory that you will learn, and I'll explain to you later, if the token itself is meaningless, but it is paying attention to all the other text, then it must, in a sense, capture the context of what is being said afterwards, isn't it? Nobody is paying attention. Nobody should be paying attention to this token in a way, or maybe they can, but it's sort of the context. It is paying attention to everything and trying to figure out what is written out there. So this token becomes important. And what people did is they would do this. They would take the CLS token vector and they would feed it through a, let's say, it's a softmax, but in this particular case, I would just say a logistic regression. People, you remember logistic regression, a basic logistic node? You would pass it through a logistic node and log it. What would it produce? Probability. It would produce a probability, a number between 0 and 1. And what you would do is you would train this, or it is trained, that if sentence 1 and sentence 2, similarity search, similarity measure, S1 and S2, how similar they are, right? If they are highly similar, the probability would be high. If they are not similar, the probability would be low. So it would become degrees of similarity. That probability would reflect degrees of similarity between sentence 1 and sentence 2. Then people said, well, amazing. And actually, the history of the field is when BERT was there, the first thing that happened is Google said, okay, good. We are the inventors of transformers and we just made BERT and now we have to productionize it. They took it to production, but there was a problem to it, which the authors mentioned in the first. The problem is this BERT is huge neural network, a massive, well, by today's standard is puny, but by 2019 standard or 2018 standard when BERT came out, It was massive. It did its job very, very well. But each comparison was 10,000 times more expensive than looking it into a, for example, search database, a simple search, Elasticsearch or something like that. Or in Google's case, compared to what they used to do using their state-of-the-art search technology. So they got a rude awakening. Oh my God, this is really very good. But oh gosh, right? We just need 10,000 times more hardware. Even Google cannot buy 10,000 times more hardware for its search, right? Or it would be prohibitively expensive. So what do you do? So here's the takeaway. BERT is very good to compare two strings, but it is very expensive, right? Let's write it down as a takeaway. And I'll just use the word BERT is an example of something called a by encoder. Why by encoder? By encoder means two sentences, they get encoded and come out. It turns out when you learn about the transformer, you'll see that BERT is only one half of a transformer. It's the encoder part of the transformer. A by for the two sentences that go in. So by encoders are excellent at similarity measure, but horrendously expensive compute wise. Not only that, latency goes up. Are we together? While you can do, and remember, inverted index searches ultimately, in a very simplified way, look up in a hash table, right? Not quite. Well, in reality, search is more complicated than that, but it's a simplified way of looking at it. Therefore, necessarily very fast. This is by no means. It would literally take a couple of 100 milliseconds to just compare two strings, right? Or actually, not a couple of 100 milliseconds, but actually, no, I take that back. To just compare one still would take a few milliseconds, but it was expensive. But now the problem is, suppose I have 10 million documents and I ask you to do, say, I tell you, go find my search results. If I give you a query, what will you have to do? The most relevant search results, how will you find? The most relevant search results would be those results, those documents, which are most similar to the query, isn't it? So you will have to create the similarity score between the query and every document DI in the corpus, right? Where the cardinality of D can be 10 million. So by the time you do that, you realize that it's become a horrendously expensive computation. Linear comparisons are terrible, right? First of all, BERT is expensive. And then to make matters worse, now do it 10 million times. Even if you could parallelize it, it's still expensive, right? To come up with a search. And then, of course, you have to sort it and pick the best. So within that backdrop, the sentence BERT paper came. And the whole theory that I explained of not using the documents directly and comparing them, but instead using, what did we use? Embeddings, vector embeddings. Convert each document into vectors. Store them. So that when query comes, what do you do to the query? Convert it to vector and just do a vector comparison. So this paper says, take the query, first convert it to a vector, EQ. Then have all your documents DI become EI vectors, right? Compare not documents, docs at runtime, but vectors. Are we together? Now, vectors, if you're doing cosine similarity, cosine between EQ and EI is far, far cheaper than passing two sentences, two docs, a query and a doc, through a BERT. Orders of magnitude cheaper. Are we together? This would work. But even now you realize that if I have to compare this query against all the documents, it's still a linear comparison, order n comparison. But then comes approximate nearest neighbor search algorithms to your rescue. What you do is, because these documents you can pre-index. Remember, documents, you know what documents you'll search from. The only thing you don't know at runtime, at inference time, is the query. User may enter anything, but documents you know. So you have pre-created the vectors. And what you can do is you can put these vectors into a ANN, approximate nearest neighbor search index, like FAS, think FAS. At that moment, the FAS wasn't out, but I'm just saying that state of the art today is not only you're doing cheap comparisons, but you're doing it even that lightning fast. Because to find the k nearest neighbors, because you see, search results has been boiled down to just finding the k nearest neighbors, isn't it? And that these vector indices do very, very fast. So today you must be hearing just about every company and every guy and his brother is doing a startup creating RAG, right? So we actually offer a course, RAG to Riches. If you go to our course portal, right? RAG to Riches, right? So it's the shortest path to wealth these days, right? So, and so it all began with this paper. It's a good place to start. What this paper now says, I'll just read it. And because I've explained everything that this paper has to say already to you, and the reason I'm introducing you is in every day I'll cover at least one research paper, right? So that you develop a habit of reading research papers and finding that they're actually very easy to read. So let's read the abstract. Bert and Roberta, which is the more uptown cousin more downtown cousin, more big brother of Bert, is just improved Bert, Roberta. Roberta is the most common use these days, the Bert incarnation. Bert and Roberta has set a new state-of-the-art performance on sentence pair regression tasks. Sentence pair means, remember, two sentences we passed, right? Why is this a regression task? Because it comes up with a similarity score, right? Like semantic text similarity. However, it requires that both sentences are fed into the network at the same time. Sentences, remember, texts are fed into the network, which causes a massive computational overhead. Finding the most similar pair in a collection of 10,000 sentences requires about 50 million inference computes, 65 hours on board. Well, today it wouldn't take that long, but in those days, yes. 65 hours to do one query. So imagine that if Google said, now, great, we'll give people the best answers. Every time you entered a query, it says, come back in 3 days. Right? So 65 hours. So with BERT, the construction of BERT makes it unsuitable for semantic similarity search, as well as for unsupervised tasks like clustering, some other things. By the way, remember the gold standard, BERT, or this bioencoders. I'll use the general word bioencoders these days. They give you excellent performance at excellent search results at unacceptable compute cost. That's the main problem. That's the problem with it, right? That's the problem with BERT, directly, using it directly for search. You can't use it for search, right? Or bioencoders. No. So that is the architecture we are talking about here. That's what I explained. In other words, do vector embedding. Use BERT to produce vector embedding and compare vector embeddings. Right? That's the main idea that this paper will propose. It says, in this publication, we present sentence BERT. Now, the word sentence here needs a little bit of a clarification. Right? I'm reminded of a statement in Alice in Wonderland, in which I don't know who it is. Alice is completely lost and says, what do you mean? And I remember, I'm trying to remember the character, says, I mean, Yeah. No, what does this mean? And says it always mean what I want it to mean. Right. So in the same way, in natural language world and processing and natural language understanding world, the word sentence is very fluid. Right? English sentences are demarcated by punctuations, isn't it? But in pictorial languages, there are no punctuations from what I'm told. Can somebody confirm that for me? Okay. So sentence in natural language can be anything. It could be a word, a phrase, a actual genuine linguistic sentence. It could be a paragraph. It could be the entire document, the entire text, right? So the word sentence, you have to take it in context. When researchers talk of sentence, they mean text, right? They mean text, any text. In this publication, we present sentence BERT, S-BERT, a modification of the pre-trained BERT network that uses Siamese and triplet network structures to derive semantically meaningful sentence embeddings that can be compared using cosine similarity. Is it all ringing a bell for morning? Yes. This is the main sentence of this. Use similarity. So what is a Siamese network? Do you know what Siamese cats are? Or Siamese twins? Siamese twins, totally identical twins. So what it is saying is that uh, we take triplets. What were the triplets? Uh, take a sentence, take a similar sentence, and take a random sentence. That makes a triplet. Siamese means compare the sentence to the similar one. That makes one comparison. Make comparison between sentence and the random one, right? So you take BERT. Remember, BERT takes two at a time. But what you do is you train BERT alternatively. You say, when I give you two similar in the triplet, put them close. The vector embedding should be close to each other. When I give you the sentence and the random one, they should be far away. The cosine distance should be high. The cosine similarity should be low, isn't it? That's all you're saying. So this reduces the effort of finding the most similar pair from 65 hours with BERT, Roberta, to about 5 seconds with S-BERT, while maintaining the accuracy with BERT. But by the way, today it doesn't take 5 seconds. It not even takes 5 milliseconds. Yeah, both are similar. That would be considered similar. So what you do is, see, this is what is called supervised learning. Namely, you have to feed it the triplets to train it. So somebody has to sit and painstakingly take a sentence, take a similar sentence, and then throw in a random. Random is easy. Just go on the web, pick a random sentence and throw it in. Are we together? You do that. Now, is this the best way of doing it? Over years, of course, more research has been done. When those of you who were there in my Colbert paper reading know that there are ways to improve this, but we'll leave it here. It reduces the time significantly because you're comparing vectors. So now let's get into it. I won't go into the fact that a little bit. Look at this. The number of computes that you have to do were enormous and blah, blah, blah. We won't go into. Let's go into what you do. Look at this. What are we doing? We are taking sentence 1, sentence 2, and finding their similarity. And then we are picking up. Now, the softmax, what is softmax? It's just a class. It will emit out a probability for you. If you have taken my Tuesday class, of course, you know what it is. But if not, it doesn't matter. Just think that it produces a number between 0 and 1 for you. Then, here's your regression objective. Did I say, what do we want to maximize? A sentence A and the sentence that's similar to it. You want to maximize the cosine similarity. And you want to minimize the similarity between the sentence and the random one. One way to minimize is to maximize the negative of that. Right? So this loss is called, it has a name, it is called the contrastive loss. And this sort of thing in which you pass in triplets with this, these are Siamese networks, because both the pairs actually went through exactly this, in practice, the same network. You pretend that there were two different networks and you train it. training details, you train it, and then after that, that's a one idea. Do you notice that most research papers have one crucial idea? That's why they're so easy to read. Unlike documents written by engineers, which are indecipherable hieroglyphics, right? Have you ever tried to read your other team's doc? Okay, so all right, guys. So we will look at S-BERT. Yeah. Yeah. The distance, the cosine, see, you want to, you're getting a cosine. That is it. That is it. That is it. All you're saying is, that's all you're saying. You're saying, let the cosine between a sentence and its similar sentence be high. Let the cosine between a sentence and random sentence be low. That's far. Exactly. That is it. Is the way I drew the picture. That is it. Right. And so, yeah, this paper could have benefited with a few visualizations like the pictures. But now let's look at that. Look at the benchmark. These are, by the way, different benchmarks to evaluate things. If you look at the benchmark, on different evaluation benchmarks, do you observe that it is, even though it performs computations much more cheaply, expensively, the yellow that I've highlighted achieves near state of the art, or sometimes beats the state of the art. If it is in bold, it's a leader. And you notice that it is very close to the leader in every other respect, in every other column. So for example, look at the first column. It is some benchmark here, 74, and you are at 72. Not bad, right? In this one, of course, it achieves the state of the art. This one, it achieves, here it is 81.5 and you are 80.99. Would you be too depressed about it? No. Likewise, you can see 76.82, 76.25. You know, we are squabbling over decimals. Mm-hmm. So it does achieve pretty good results. Then there are more benchmarks here. I won't go into all of that, but suffice is to say that benchmark after benchmark. So this is how research papers are written. They contain an introduction. They mention other people's work, prior work, essentially to say we are better than them, eventually. No, I'm kidding. Right? But to put the context, background, and then you show your method, and then you prove that your method worked. So this is proving the method works. These are all the papers. And as you can see, you can take any benchmark and you can see it's doing well. Would you agree? It's doing very well. And ablation studies are important. What does ablation study mean? In our field, we do ablation study. Ablation study means what if you took some of the, suppose you bring 3 ideas to the table in this paper. How much would you lose if you threw one idea out? Suppose you threw an idea out and your model still did great. What would that mean? It would mean that idea was useless, isn't it? So every idea needs to be a key player, key contributor to making for success. In other words, it's cooperative gaming. They all need to contribute strongly. So that you do through ablation studies. So this is it. Do you realize how easy it was to go through this? No? Now, papers are usually much easier to read. Trust me, I find reading corporate engineering docs much harder to read than papers. Yeah, go ahead. You'll learn because we'll cover see, what I've done is I've flown over some territory because today I want you to get hands-on, start doing projects. From next week onwards, I'll come back to the core, the foundational revolutionary paper. Attention is all you need. And then we'll do BERT. And as we do those 2 papers, you'll develop the foundations. Basically, the CLS, I suspect, is a name, it stands for classification. Right? Okay, guys. So that ends our paper reading. If you compare this, what I explained to you and what I have been doing in, is this what I have been explaining to you guys? That's it. Go ahead, Abdul. No, no. See, the Siamese network is sort of a conceptual way of thinking about it. I have two pairs, two sentences that are similar, two sentences that are dissimilar. So A, let's say that A, B are similar, A, C are dissimilar. So I sent this pair and this pair both through the network. But you pretend as though you're sending them in parallel because you can send them in parallel, right? So you pretend as though they're going through two networks. That's it. It's a pretend thing just to explain to people. In reality, you're sending them through the same network. And when you're training the network, so what happens is that, see, what you're doing is you're taking BERT, but you're not using, but you're retraining BERT to become smart at producing good embeddings, semantic embeddings, through the contrastive laws or triplet laws. That's the core idea of this paper. Using the triplet laws, you do that. Now, over the years, this paper has become sort of the baseline, and many improvements and things have happened. In particular, just this Wednesday, the paper reading that I did makes significant improvement. I'll post that paper reading also, the video of that also, for you to go through in case you have the time. Right. So that ends our paper reading. I hope now you get the main foundation behind semantic search that we are using. I invite you very seriously to please go and read the documentation on this website, SBERT. Right? Now, this is sentence transformers. Right? One of the key pillars today of generative AI and all the activities that we do, become very familiar with it. The more you know these things, the better. But now it leaves us with one question, getting back to practicals. Hey, what about the fact that this sort of slightly underperforms the gold standard, but directly, without this cross-train, without this embedding triplet laws? If I just take a bi-encoder, I told you the bi-encoder will do a similarity search slightly better than going the indirect way of first converting them to vectors and then comparing vectors. It just is expensive. So how can we have the cake and eat it too? Right? So here's the trick we use. What you do, and that brings us to re-rankers, the topic of re-ranker. Well, let me add it as a separate topic and teach. Oh, no. Re-ranker. It could be a little fatter. Suppose you have a massive amount of documents, let's say 100 billion docs. You don't want to do a comparison, right? What you want to do is convert them into vectors, embeddings. So you have that. Given a query, you can dip into it. You can come back with, it will return your k nearest neighbor, let's say 20, k nearest neighbor, KNN, say 20, or let's say even more, let's say 40 candidates. These are your search results. You can just emit this out to the user as you are doing in your early parts of your project. Alternatively, what you can do is now you can say, let me bring back that gold standard. I don't trust this result. Given this query, I now compare it with each of the results Ri. I do a similarity search. Yeah, using a bi-encoder. Right. Are you together? Even if you got 100 results, see, this vector-based search has to be just good enough to make sure that all the meaningful results are somewhere there in the 100. And 100 is a large number. How many times did you ever scroll down to the 100th Google search result? Right? So you do that, you go to the similarity, because you can trust that you can pass it through a BY encoder. This BY encoder is called a re-ranker, because that's literally what it is doing. It's re-ranking, isn't it? And so it will bubble the best ones to the top. Is it expensive? Hey, if I'm just doing 100 comparisons as opposed to 100 billion comparisons, I have an order of billion compute efficiency, isn't it? And so you just had your cake and ate it too, right? While you are at it, let's bring one more idea. We are feeding this from vector search. Why not sneak in things from keyword search also? Because how would the bioencoder is a bioencoder, re-ranker is a re-ranker, keyword search, because we know that sometimes people may just enter a bit of keywords and AI search might not do so well. So you can take your Elasticsearch or Solr, whatever, and the search results for that also, you can mix it up and give it to the re-ranker, isn't it? And when you do that, you create what is the benchmark, is the right way of doing it, actually. This is the hybrid search. You just did hybrid search. You got it, right? Because how does it matter whether you got those candidates that you're feeding into the re-ranker came from vector search or came from Elasticsearch, right? Keyword search. Re-ranker will just re-rank it because it's doing that expensive computation on just 100 or 50 or 200 or whatever it is, number of comparisons. And it can run through those comparisons very, very efficiently. So I'll take questions in a minute. So one of the things that is happening these days is there is this sort of architectures are becoming very, very useful, right? For example, this is a part of RAG. People have improved the efficiency of this to such an extent that, for example, companies like Grok, G-R-O-Q, right? They do ASIC. They have boiled the transformer inference part of it into the silicon. They baked it into the silicon, right? And so they run some of these inferences. Actually, they do it for an LLM, the full transformer, the chatting kind of thing. But people are beginning to do it. Grok has done it for the chatting kind of thing, which will generate text. But people are now baking in transformer down to the silicon. When you bake it down to the silicon, you realize that the efficiency you gain is tremendous, right? These re-rankings are not going to cost you much. Well, they don't cost much anyway, right? If you're just doing 100 comparisons, it's cheap. Or 50, you're picking top 5 out of 50, cheap. You can literally send a batch of 50 at one go. Batch size of 50 at one go and get your results out, right? The mini batch size. Literally get that, or 50, or maybe 2 batches of 32, or whatever it is, 32 in it, and get the results. So very quickly you can get the results in 2 real computes. This is the way to do hybrid search. And why hybrid search? There are situations in which if the query is not semantically meaningful enough, keyword search will beat semantic search. So to recap, we learned about semantic search today. We learned that it does, when the query is rich semantically, it tends to beat keyword search. But just to safeguard it, why not take the best of both the worlds, put a re-ranker? Re-rankers tend to be a bit expensive, but not when you just give it 100 or 200 or 50 queries. I mean, if it is just 1 or 2 inference batches, because you always pass data in batches, mini batches, it can just go through in one payload. The vector search, on the other hand, is extremely fast, is cheap. When you put it together with ANN, any approximate nearest neighbor algorithm for vectors, which have a long history of maturation over the last 30, 40 years of development, it is lightning fast. So you would be surprised. Most of the things that you use these days, if any retail thing you're doing is using recommender system, most likely baked in the recommender system is this somewhere. You're using Spotify, you're using this, whatever. Obviously, I'm not privy to anybody's secret stack, but it is almost a near obvious guess that 90% of people, companies, are baking it in to their core architecture, what I just taught you. And the fun that you'll have is you'll build it from scratch, so you'll know how to do it. Right? Questions before I stop this, and then we'll go to the last phase.
As if the 100 billion docs, the query that went in.
Yeah.
How many comparisons are happening there actually to produce the top?
It depends upon the indexing technology. Within FAIRS, you see the whole point of the magic word is approximate.
Yes.
We will do the meaning of that word later in a whole session. But basically what it means is you do very few comparisons.
Mm-hmm.
Very few. Like when it goes in and compares vectors, usually perhaps in the order of 100 vectors at most is comparing, or even less. It zooms in pretty quickly, 20, 30 vectors, and it's pulling out the search results very quickly.
From the 100 billion docs.
Yes. And see, that's the whole technology. This approximate nearest neighbor search has had 30, 40 years of evolution. They are used not just in machine learning AI, they have been there in existence for a very, very long time in computer science. And you're literally leveraging decades of development.
Mm-hmm. Yep.
That's that. Guru.
The similarity. Sorry, yeah.
Please hold on. I'm getting a question in the audience here. That is right. So not only are vector comparisons cheap, you're comparing against barely 50 or 100 inside the pass. So keyword search also works the same way. You give the same documents or chunks, and what it will do is it will shred it. Remember how I mentioned keyword works? It will do the hash table. Roughly speaking, it's a very simplified version of thinking about it, but that's what they do. They create this table, right? And you just look up the table for the keywords. Yeah, both the results you feed in, and it can be very fast, right? So from whatever public information we have, for example, Google and all of these big guys, when your query, it goes through, it isn't that you just use one technology. It goes through a whole slew of things. It's sort of a scatter gather. And then you put it together, re-rank it, and so forth. TikTok, all of this is there. How many of you have found that you or your kids are addicted to TikTok?
Mm-hmm.
Yeah. So, well, believe it or not, all of these, you're beginning to meet the culprits now.
Mm-hmm.
Okay, with that, and so all these great algorithms, right? This technology that I taught you is so central and so important. It's hard to find a state-of-the-art technology in production, enterprise-grade production, that in one way or the other is not using this. Very, very dominant.
That's it. A quick question on that. A quick question. If you go back to the last picture you drew, re-ranker.
This one?
Yeah. Yes. So the re-ranker that I understand the keyword search getting added, but the sim between the Q and the R, why didn't the earlier box already do that?
No, you didn't get it. So okay, let's go through the process. You give it a query text. The cow jumped over the moon. Query is cow jumped over the moon. This is your query. This gets transformed to a query vector, EQ.
Query vector, yes.
EQ is given to ANN. What will ANN return? ANN IDs, document IDs or chunk IDs.
Mm-hmm.
From that, you can get the text.
Okay. You got the text back. Okay, got it. Now you got to vectorize it now.
Yeah. No, you don't vectorize it. Remember, re-ranker by encoders don't take vectors, they take text. S1, S2.
Yes.
So now you can take the query, you can now you can keep this fixed, query fixed, and you can pass on this one by one and keep getting the scores. Score comparing Q versus each of the text here, right? To do a better re-ranking of that. This is your re-rank. Oh, yeah. See, when the text, a list of texts you got, sneak in your keyword search also. Because what will keyword search produce? Also texts. No, here's it. I said the cow jumped over the moon. So keyword search may produce something like the cows are grazing. Exactly. Right. So it's, you just give it to both of these. That's why I made this picture. Where are we? We lost that one. Okay. Somewhere here. Yeah. Like you, anyway, somewhere I made the picture, I've forgotten where. Oh, in my phases, yes. In my phases. There it is. Phase 7. Do you notice that? The query goes to both, produces candidates. Those candidates you pass through a re-ranker. Make sense, guys? All right.
Yes.
Okay. So
can you show the last picture? The last picture again, where you're sending the sentence and the query back again. Yeah.
You mean this picture?
Yes. Great.
Okay.
Excellent.
That's right. So guys, I will pause here. Half the day is over. Let's start.